reservations in two-way slabs by means of yield lines. In this video, we will deal the cases where two sides of the slab is fixed and two other sides are simply supported. We have in total 5 cases from case 11 up till case 15. This is a general plan view of a slab to indicate the different types. And type 11 to 15 is, of course, in the right hand bottom and on the top left. The green color means fixed or continuous, and the orange one is simply supported. Now let's consider a rectangular slab with a size A and B, where B is always bigger than A. Using the 30, 45, 60-degree rule, we know that when the one hand is fixed, this is an angle of 60 degrees and the other one is 30 degrees. We also know that this is an approximation, but it is fine to use this approximation. This is 45 degrees because both sides have the same condition. You have also the yield line because of the negative bending moment. I call negative bending moment the bending moment which gives tension in the top fiber of the slab. And then we can make the connection between the two yield lines. And there is also a yield line for the negative bending moment. Then we can go to the geometry. This is distance S1, and S1, of course, by the Tangens rule or the cotangens rule, is the A divided by the cotangens of the two adjacent angles. It gives you A over square root plus 1. S2 is, of course, the same as S1 because of the angle of 45 degrees. And S3, again, we will use the cotangens rule, and we have this relationship for S3. And S4 is equal to S3 because this is 45 degrees. So we have S1 equals S2 and we will now look deeper into the yield lines. We have the positive bending moment, which means that the bottom fiber of the slab is in tension. We call it M. The negative bending moment, we call it M1, and on the other side M2. You can now fill in the relation between N and M1 or M and M2. Or what we consider is that because most of the time the reinforcement top and bottom are equal, so this means that the plastic bending moment is equal in top and bottom, so M is equal to M1 is equal to M2. The work done by the external forces is a summation of triangles and rectangles. For the triangles, we got S1 multiplied by A plus S3 multiplied by A. So all the triangles together is your good term. And then you multiply it by delta over 3, the mean deflection. For the rectangular section, we got A times this portion, which is, of course, B minus S1 minus S2. And we multiply by the mean deflection, which is delta over 2. Then we can fill in S1 up till S4, and we obtain this equation. We look now at the work done by the internal forces. We start from this side. This is the bending moment projected to this axis of rotation, which gives you M times A, and the angle of rotation is delta divided by S1. At the other side, we got M times A times delta over S3. Then we got the M2, which is of course M2 times A, and angle of rotation delta divided by S3. For B, we got M multiplied by B divided by 2. And in the other side, we have M projected to this axis of rotation and multiplied by delta over 4. And of course, the negative bending moment M1 will do B times M1 times delta divided by S4. We can again substitute the different variables and we have this equation. B, of course, must be equal to E, and then we find a closed form for the bending moment M, and M here in this case is then equal to this formulation. We call it M0 because this is the maximum bending moment without a hole in the slab. So that's your initial state. So that's why you call it M0. It's only a function of the load and the geometry. Now let's do a check. Let's see what does that give for a square slab. It means that A must be equal to B. We take the formula of M0 of the previous slide and we find this equation, which is more or less 2h squared over 35, which corresponds well with literature. For the further calculations, we will use Ex, which is just E divided by delta over Q2, or delta of E divided by the deflections times the load, the unit load. And Vx we define as V divided by the deflections times the bending moment. So when E is equal to D, then of course M is just Q times E over X over dx. And we will use the property bearing capacity, which means if the bearing capacity is bigger than 100%, then making a hole in the slab does not lower the total bearing capacity of the slab. If it's smaller than 100, then we can not put as much load on it as was initially meant to. For an existing slab, for instance, when the reinforcement is equal to S0, 0 for existing, we know that M is proportional to the load. This factor C is, for instance, something like that. And we know that M0 is Q0 times C0. So when you play a little bit around, you will see that the bearing capacity was given by this formula 100 M0 divided by. Now we will look at case 11. Let's look at case 11. Case 11 is a rectangular reservation in the slab with a size of D1 by D2 and the position D3, D4. To be a two-way slab, B must be between A and 2A. The horizontal position of the slab, of course, the reservation must be between S1 and B minus S3. So this is this reservation going, sorry, this reservation going from left to right. D4 must be equal to, must be smaller to S1. So this means that this reservation cannot surpass this point here. So D4 is smaller than S1. D4 is smaller than S1 divided by S4 times D3. It means that this tip is lower than this yield line. So this is lower than this yield line. And for the vertical position, we say that S4, or let's say D1 plus D2, so from there to there, will be bigger than S4. So one tip of the reservation must be below this line. And D3, of course, must be smaller than S4. Now, by using those conditions, we have defined a typical reservation is 11. Now let's look And this reservation case 11 with different examples. When you vary the parameter D1, D2, D3, and D4, you can have different conditions like this, or in the corner, or like that. So it gives you an idea what the case 11 reservation is. Just take care that the case 11's reservation on the left-hand side, those two corners of the reservation must be within the field line, and on the other side, it must be on the outside of the yield line. So, for instance, this case is not valid. Those 2 points are on the outside, that's okay, but those 2 points are on the inside. So the formulas that we are going to produce is out of the scope of this case 11. Now we know that there are conditions on case 11. We have filled in the different variables S1 up till S4, and then these are the numerical conditions on the reservation. Now let's look a little bit deeper into the geometry. On the left-hand side, you see where the reservation is cutting the yield line. This distance is called x1. So don't mix up with the distance d4. So x1 is from the yield line until the axis of rotation. Same for x2 and y1. So then we see from the geometry of this yield line, and this is 60 degrees, it means that x1 is equal to d3 divided by the square root of 3. X2 is of course equal to y1 because this is 45 degrees. So, and it's equal to a minus d3 minus d1. Now, when we are calculating the work done by the external forces, we have to multiply by the mean deflection. When we look at this particular case, then you will see that when this piece of slab, this rotation x has a deflection here of delta, then of course on a distance x, the deflection will be proportional to the distance. It means that the deflection there will be delta over sy, or in this case, x over s1. So you must not forget this proportionality rule. Then we know that this deflection on this side is, of course, delta times d3 over s4. The deflection on this side is delta d4 divided by s1. And on this side here, this tip is delta y1 over s2. We can now try to calculate the work done by the external forces. We know that it is a summation of triangles, which is the light green one. We have also triangles, and then there. And the summation of the rectangulars. We have different types of rectangle. First this one, then you have this rectangle, this portion, and this portion. Now, looking at it like that, it's getting easy to write down the formula together with the parameter x1, x2, and y1. Then we will see that the work done by the external forces is then equal to d4 times d1 times the mean deflection. The mean deflection, of course, now is this on the tip, which we have seen in d4 divided by s1. And it's the mean deflection is half of it. It's half of the maximum deflection because it's a rectangle. Then we can proceed with the yellow elements. This element is d3 times, of course, d4 plus d2 plus d4 minus x1, and times the deflection, maximum deflection here, which is d3 over s4, and then divided by 2 for the mean value. And so we can continue for this rectangular, this one, this, and then the biggest one at the end is, of course, a times this piece, which is b minus D4 minus D2 minus S3, and then multiplied by delta over 2. Then we have the summation of the triangles, the green portions. We see this is A times S3, that's easy. And then we got on the corner, we have 4 times, in fact, depending on the different values. And the mean deflection is x1 over s1, b3 over s4, y1 over s2, and x2 over s1. So this is just this triangle projected to this axis, this triangle projected to this axis, this to this one, and that to this one. And then you arrive at this formula. We can fill in the different values, but it's a formula that is not very practical to use. So we will have a variable which we call h2, and h2 can then be written as this. h3 is this expression, and it the work done by the external forces is then equal to a combination of h3, h2, and so on. So this is more practical to use instead of one big large formula. The work done by the internal forces is then equal to, if we look at this yield line, which is M times B divided by S4. So because we are working with dx, so it's B divided by S4. This yield line is interrupted by reservation, so we have a total projection to the axis of rotation, which means B, but we have important B4 minus B2, which is not there. So it's this part. This part. So you see that this B4 plus D2 is subtracted from it, and the angle of rotation is delta over S4. Then we have x1 from there to there. It's x1 projected to this axis, so it's x1 divided by S4. Then on the bottom, you have B minus D4 minus D2 divided by S2. And then for this, we have this value x2 divided by S2. And what's left is A, this orton A divided by 3, and D3, this value correction to this axis of rotation means D3 divided by S1. And we got the same on the bottom. This is Y1 divided by S1 projected to this axis of rotation. So, and then of course, the last one is this. Then we can fill in the different parameters, and we arrive at this formula. We know that the bending moment is q times ex over dx, and these are the conditions to use the formula. Otherwise, you must use another formula. These are the limiting factors. Now let's look at an example. We have a rectangular slab 6 by 8 meters. The thickness is 20 centimeters. Concrete cover is 30 millimeters. The floor finish is 2 kilonewton per square meter, and a mobile load of 11 kilonewton per square meter. We have this slab, which is continuous on those two sides and simply supported on the other side. And we have a elevation of 1.2 times 4.2, the distance 3.3 meters. Now, what is the needed reinforcement of this slab? We start with calculating the load in ULS, which is the permanent load times 1.35 plus the mobile load times 1.5 gives you 26 kilonewton per square meter. These are the different parameters of the slab. We calculate S1 equal to 2, that's 2.2 meters. We calculate S3, which is 3.8 meters. Now we have almost all variables. Then we have x1, x2 equals x1, and now we will have all variables. We will check first if we can use the formula, the correct formula. So we look at the horizontal position. We know that this is the condition. So if you fill in the different parameters, you will see that this is right. 4.2 or 4.196 is just an error in accuracy. So that's okay. The 4 must be smaller than 0.36a. Okay, this condition is fulfilled. The 4 must be bigger than, it must be smaller than 0.577 d3. This is also fulfilled. Vertical position, we know that this condition must apply, and when we put in the numbers, you see that this condition is okay. And the same happens with this condition. So this states that case 11, we can use the formulas of case 11. The maximum bending moment is then, assuming that, of course, the top and bottom reinforcement is equal. We can calculate from the previous slides H2 and H3. Then you can now calculate the work done by the external forces. It's 14.6. And the work done by the external forces, by the internal forces, is 11.36. And the bending moment is then dx divided by dx times the load. And we got 33.35 kilonewton meter per meter. So you see that you can rather very quickly calculate the maximum bending moment without using any final elements, finite elements. Then we now have to convert it into reinforcement. The lever arm X is then total height minus the concrete cover minus the point of gravity of the reinforcement, and it gives us 165 millimeters. I assume the diameter is 10. If not, I will redo the calculation. The lever arm in the other direction, and then we calculate the mean lever arm, which gives us 160 millimeters. So the needed reinforcement by definition is then 1.1 because it's an upper bound method times the maximum bending moment divided by the lever arm 0.9d divided by the yield stress of the steel. It gives you 586 square millimeters per meter. So this is a diameter 10, a mesh of a diameter 10, 8 per meter. Will be okay. So this is the reinforcement up, bottom, X direction and Y direction. So 4 times. We will now give another example. It's an existing slab with top and bottom reinforcement equal. We do not know what type of reinforcement is in it, and we do not know the design load of the slab. The question is asked, can we make a reservation 2.8 by 1.8 in the bottom left corner? We can calculate the maximum bending moment without the hole, assuming that the reinforcement which is there properly calculated. And because we do not know the load, we divide the bending moment with the load, and we have an expression which is only dependent on the geometric characteristics. And when we calculate this, we find 0.755. The maximum bending moment with the hole, then we can also calculate m divided by z by q, and you would arrive at a formula which is only dependent on the geometric properties. We calculate h2, h3, and we can calculate m over q, which is 0.789. So we see that now the bearing capacity is 96%. So by making this reservation, we will have a small loss in bearing capacity of only 4%. So without knowing what reinforcement is, we can decide if this reservation can be made, yes or no. Demonstrate how to use those type of formulas. I will give you an example. You have a rectangular flap with case 11 reservation in it. This reservation moves from the bottom left corner up until a higher position. And we will ask ourselves, what is the best position of this rectangular hole? It can be a reservation for a ventilation shaft or something like that. So is there an optimum position, yes or no? We look at the reservation. The parameter B4 is then equal to alpha 4 times A. So in this video, we will work with dimensions. We will work often with dimensional units or dimensionals as parameters. So it's always divided by the smallest size of the slab. So alpha 4 is D4 divided by A. A is 4 meters. So alpha 4 is a parameter going from 0 to 0.22. B is 8 meters. The reservation is 1.6 times 1.5. And D3, which is this distance, A minus D1 minus D4, and D3 is 2.4 minus 4 times alpha when you put in the known elements, the known dimensions. So now, with those, in this particular case, we can calculate S1 and S4. We check the horizontal position, is it all right? So we know that we have fulfilled this condition. You fill in S1 and S4, and you arrive at this inequality. You work it out, and you see that alpha 4 must be between those two, so that's okay. D4 smaller than S1 gives you this condition. D4 smaller than S1 over S4 times D3 gives you this condition. And for the vertical position, we have the condition S4 smaller than D1 plus D3, or this is the condition. And then at last, we also have this condition. So now you see you have different conditions on alpha 4, and we can see which is the most severe condition. It's, of course, alpha 4 smaller than 0.22. So this is needed for our formulas. The bearing capacity in function of alpha 4, we have seen that in the previous slides. We fill in the different known elements and we got this equation. Put it into a graph alpha 4 from 1 to 0.44. Remember, this formula is only valid up to 0.22. And on the y-axis, the bearing capacity, which is the red curve, which is in fact this. The blue dotted line is just a simplified fitting, telling that it's almost linear until alpha 4 is equal to 0.11. Okay. So now we can calculate the different positions. When alpha 4 is 0, so it's this point there, you get a bearing capacity of 94. So it means by making in the corner the reservation, you lower the bearing capacity of the slab. When you are somewhere here, the bearing capacity is 97%. So it means this is this point here. And it's when the reservation is on this location, the bearing capacity is 98%. So we see from this exercise that the more you put the reservation to the middle of the slab, the better it is. You still have a shortage of 1.6%, but that's not very important. But you know, the best position is to move it to the center and not to put it on the side. We can have now another example for an electricity panel. For instance, you have a concrete slab. You have to make in a reservation this size, and now we want to know what is the effect on the bearing capacity of the slab. So you will have a reservation from there to there, or from here to there, or from there to there. So that means that D2 is varying from 2.2 meters up to 5.2 meters, or d2 divided by A equal to alpha 2 between those two parameters. Now I want to know what is the influence on the bearing capacity of this type of reservation. So we summarize it. You have two extremes. Alpha 2 equals 0.367 and alpha 2 is 0.866. So this is the variation of the reservation. E is in our example 6 meters, B is 9 meters, B it's 1.5, D1, so that's 1.5 meter. And D3 is from there to there, it's 3.6 meters, and D4 is 0, so it touches the edge. And the parameter, of course, is V2, and it's 6 times alpha 2. These are different parameters. This is S1 and S4 in this particular case. We check if it is at case 11 reservation. So we check the horizontal position, fill in D2 and D4. We arrive at this condition. This gives you this. Then we do it for all conditions. This is okay. This is also okay. The vertical position, you see that S4, the 3.804 must be smaller than D1.6 plus D3, 3.6. So that's this. This is also okay. And the last one, this is also okay. So what's left, if you look at this, you see that this is the most severe restriction. So forms are only valid for alpha 2 between those two values. And it is a case 11 reservation. We can now calculate the bearing capacity in function of alpha 2. This gives you this formula, and you can put it into a graph. X-axis is alpha 2, and the bearing capacity is the y-axis. You see, it's almost linear. And for the different cases, we see immediately that it's always below 100%. So it means that if you make a small hole like that, small reservation like that, you always lose bearing capacity unless you do not cut the yield line. So if you do not cut the yield line, you keep the bearing capacity. But by cutting the yield line, you lose bearing capacity. So it's not necessarily the surface of the reservation that makes it more severe. No, it's the parameter that is most important is, are you cutting yield lines, yes or no?